Hey Chem 2A, I had a last minute request to go over the Chapter 4 homework. So I'm going to go through them very quickly. Keep in mind some of this is stuff like some of the numbers you can look up or calculate yourself. So there might be some numbers you have to figure out where they came from, but I am here if you have questions. So the first question is you're told nitrous oxide has this mass, reacts completely with an equal molar amount of NO2 to form elemental nitrogen and oxygen, and we want to know how much N2 is formed in the process. So our first step here is to write the general reaction. Nitrous oxide, we're told, is N2O, and it's reacting with an equimolar amount of NO2 to form, that gives us our arrow, N2. Elemental nitrogen. So elemental nitrogen, remember, is one of those diatomics. Same with oxygen. So these are N2 and O2 that it's forming. So the next thing you have to do is you have to balance this equation. You have to make sure it's balanced. I've gone through it in my lectures. It's not the easiest thing to kind of teach, but I'm just going to go ahead. So I'm just going to go ahead and give you guys the balanced equation here. And then you can go through that and kind of practice the balancing yourselves. But if you need more help with that, just let me know. So we are looking for the amount of nitrogen. And so this is a stoichiometry problem. We're given grams of one of our reactants of nitrous oxide, but we can't go grams to grams. If you remember, we have to use moles to convert amounts in a chemical reaction. So we need to go ahead and take these grams of nitrous oxide, convert them to moles, and then we can compare moles of reactant to moles of product, and then finally go from moles of product to grams of product. So we have 4.77 grams of N2O. And our first step is to convert this to moles. And so to go from mass to moles, we need molar mass. So you have to calculate the molar mass of N2O. And so when you do that, you need the molar mass of nitrogen, and you have two of them, plus the molar mass of oxygen. And so when you add those all together, and you can always look this up to check your work, you get 44.02 grams per mole. So we need grams to cancel, so that means that we need the mass on the bottom. So this needs to be 44.02 grams of N2O on the bottom. And so 1 mole of N2O contains 44.02 grams of N2O. So we can see grams N2O cancel here. And so now we have moles of N2O, and we need to go from moles of that to moles of N2. So this is where we need to use those coefficients. And we see that we make 3 moles of N2 for every 2 moles of N2O. So we see mole N2O cancels. Got to get rid of those units. And then lastly, we need to go from moles to mass, and we're going to use molar mass now of N2. So that is twice the molar mass of N2O, or sorry, not N2O, just N of N. So that comes out to be 28.02 grams per mole. So we have then 28.02 grams of N2 for every 1 mole of N2. So those cancel out. Pop all this into your calculator, and you're going to get 4.55 grams. Now, when you're putting this stuff into your calculator, there's different ways you can do it. Some people, what they do is they do all the top multiplied by each other, and so then they have like one number on top, and then they do the bottom, all the bottom multiplied times each other, and then they do top over bottom. You can use parentheses in your calculator. It really doesn't matter how you put this into your calculator, whatever works for you. Doesn't matter to me. Just show your work on your exam so I can see what you did for partial credit. Okay, number 2, what is the mass percent composition of oxygen in a compound having the empirical formula C11H12O6? So we want to know how much percent of oxygen in this compound. We're given the empirical formula. So our first thing we should really do is get the total mass of this compound. So the total mass we're going to have is going to be 11 times the molar mass of carbon, plus 12 times the molar mass of hydrogen, plus 6 times the molar mass of oxygen. So it's just those coefficients times the molar mass of each part of them. So then that's 11 times 12.01 plus 12 times 1.008 plus 6 times 16.00, and so you get a total mass of 240.206 grams. So our percent oxygen is going to equal the mass of oxygen that we have divided by the total mass times 100. So our mass of oxygen is 6 times the 16.00 because we have 6 oxygens divided by 240.206 times 100, and so that gives you 39.97%. Number 3, we want the total mass of oxygen in 7.67 grams of iron 3 oxide. So there's a couple parts to this. The first thing we need to do is get the actual formula of iron 3 oxide. So we're told iron 3, so that means our iron here has a charge of 3+, and then oxide, so that means oxygen is our anion, and oxygen has a charge of -2 or 2-. So that we can do our nice crisscross trick and get Fe2O3 for our formula. So that is going to help us tremendously because we have 7.67 grams of now Fe2O3, because now we have the formula to be able to calculate or to find our molar mass. And so the molar mass of iron, because remember we have to go, you can't go grams to grams. We have to, even if it's all in the same compound, we have to use moles. So we need to convert this to moles. In general, that's always going to be a safe step with these types of problems. If you're given grams of something, or really anything for that matter, convert it to moles. It's always a safe step. So we need to go from grams to moles, so we need to have moles of Fe2O3 on top, grams of it on bottom. And the molar mass of it, when you calculate it, it's 2 times iron plus 3 times oxygen, and that comes out to 159.7. So we can see grams cancel. And now we can use our formula to see that there are 3 oxygens, or 3 moles of oxygen, for every 1 mole of iron 3 oxide. For every 1 molecule of iron 3 oxide, there's 3 oxygens, so we can scale that up to use moles. And then lastly, we need to go from moles back to grams for oxygen. So that's going to be 16.00 grams of oxygen for every 1 mole of oxygen. Molar mass never goes away. You are going to use it all the time, so make sure you really understand how it works. And so I get a final answer of 2.31 grams. Number 4, we're told the fuel tank of an automobile contains 71 kilograms of gasoline. If it reacts completely with excess oxygen to form CO2 and water, what is the total mass of the products? For simplicity, assume gasoline is 100% octane. So we need to write our reaction first, and this is C8H18 plus O2 reacts to form CO2 and water. CO2 and water, remember, are always the products of a combustion reaction. I'm going to go ahead and give you the coefficients for everything. There is a trick to balancing them. I think I talked about it in my lecture for balancing these combustion reactions, but I don't really ask you to do that. If you have questions, you want to know the trick and I didn't post it, just ask me and I'll show you. But one thing that we do know, conservation of mass, that the mass of our reactants is equal to that of the products. So we can just calculate the total mass of our reactants, and that'll tell us the total mass of our products. So we already know how much octane we have. So let's just kind of write this out. So we know that we have 71.0 kilograms of C8H18, but we don't know how many kilograms of oxygen to give us our total. So we need to figure out how much oxygen reacts with the octane, and we can use the stoichiometry to do that. So let's start with what we know, 71.0 kilograms of C8H18. And let's go ahead and start by making this into grams, because we don't really have a molar mass using kilograms. And there's 1,000 grams per 1 kilogram. I'm just going to write this as C8H18. Kilograms are gone. And to compare things, again, we need to go to moles. We cannot compare with mass So we have to get the molar mass of C8H18. And when you calculate that, you get that it is 114.23 grams per mole. And we need grams on bottom. So that means moles have to go on top. Okay, and now that we have moles of C8H18, we can convert this to moles of oxygen. And we need 25 moles of oxygen for every 2 moles of octane, C8H18. And then now we have converted to moles of oxygen, and notice it's O2, not O. So now converting back to mass of oxygen, this needs to be 2 times the molar mass of O, which is 32. So 32 grams of O2 per 1 mole of it. And then your answer, they want your final answer in kilograms, so we need this to be in kilograms. And there's 1 kilogram per 1,000 grams. So we wind up with kilograms in the end. And when you plug all those in, you get 249 kilograms of oxygen. So then our total mass is equal to 71.0 plus 249, and so you get 320 kilograms. And that is the total mass of our products. Notice it's not asking for mass of just CO2 or just water, which you could still solve for. It just wanted total mass of all your products. All right, and lastly, number 5. Acid rain is caused in part by burning coal that contains sulfur impurities. This is more of an East Coast problem. When it comes to coal, we don't really do much coal burning on the West Coast. The sulfur is converted first to SO2, which reacts with oxygen and atmospheric moisture to produce sulfuric acid, H2SO4. If a particular coal contains 0.8% sulfur by mass, calculate the mass of sulfuric acid produced by burning a metric ton of the coal. So the first thing we need to do is figure out the mass of sulfur that is produced from 1,000 kilograms of coal. And we're told we get 0.8%. So that means we have 0.800 grams of sulfur for every 100 grams. We can say grams or kilograms. We'll say kilograms. So we make 0.800 kilograms of sulfur for every 100 kilograms of coal, right? And so we also know we can just set this equal to, we make some X kilograms of sulfur for every 1,000 kilograms. So this is kind of like back in the algebra days doing cross multiplying, and you get that we get 8 kilograms of sulfur from 1,000 kilograms of coal. So now we can use this amount of sulfur to get our amount of sulfuric acid. So let's start with what we have. We have 8 kilograms of elemental sulfur. And let's start by making, whoopsie, didn't mean to push that. Keep annotations. Okay, anyway, let's make this into grams first. So we have 1,000 grams for every 1 kilogram. And then what's our safest bet? Make it into moles. We get 1 mole of sulfur, and then we look up its molar mass. It's just elemental, so 32.07 grams of sulfur. And then from looking at the formula for H2SO4, we see that there's 1 mole of sulfur. Oops, that needs to go on bottom because we want to cancel it out. 1 mole of sulfur, that's in 1 mole of H2SO4. So mole sulfur cancel. So this is how we can go from the amount of sulfur in sulfuric acid. And now we want to go from moles of sulfuric acid to grams. And its molar mass is 98.086 grams per mole. So we have 98.06 grams per 1 mole of H2SO4. And then we want this to be in kilograms, 1 kilogram per 1,000 grams. Oops. And so we get a final answer of 24.5 kilograms of sulfuric acid. It doesn't sound like much, but sulfuric acid is a very, very strong acid. I have a memory from undergrad of some concentrated sulfuric acid, a drip of it getting on my gloves I was wearing, and I could literally feel the heat of it eating through the gloves. Crazy stuff. All right, that does it for the Chapter 4 questions. If you have any follow-ups, please just text me or email me or come to the open office hours. And I hope you guys are staying safe, and I'll see you soon.